Alright, good afternoon everyone. Sorry about the small delay, wasn't feeling too well, but we'll start the class now. So today is the second, right? 2nd of October, so we will be moving on to a new topic called resonance structures. So our students who I just double checked whether I have copies of the tudes, I'll give you the tudes coming week, right? Sorry about that. So others who have the tudes, you can have it, but please listen to what I have to say here rather than focusing on the tude. So the topic today is resonance structures. Resonance structures. A resonance structure is a structure, or we say when it comes to certain Lewis structures for certain molecules, we can have more than one Lewis structure. Can have more than one Lewis structure for that. So at that point, we call them resonance structures. Such a simple thing. Now, for example, if you take something like ozone, first of all, we'll take a small heading. We'll start with a small heading. Write in your writing books. A new heading: resonance structures. Resonance structures. Resonance structures. For certain molecules, you can write for certain molecules. For certain molecules, we can draw more than one stable Lewis structure. For certain molecules, we can draw more than one stable Lewis structure. More than one stable Lewis structure without changing its main skeleton. These different structures that are drawn for the same molecule are known as resonance structures. These same structures that are drawn for the same molecule are known as resonance structures. You can write in all the different resonance structures, number of bond electron pairs added to the number of lone pairs should not change. Right. Now, as an example, please take this down. As an example, please take this down. Ozone. Now students, after taking this down, we'll continue. Are we done? Right. So here we have already learnt about drawing Lewis structures. Now if I ask you to draw the Lewis structure of ozone, couple of you will draw the Lewis structure like this, with a double bond between this oxygen and this oxygen, or oxygen in the center and the oxygen onto the left hand side. Some of you will draw it like that. Some of you will draw the double bond between this oxygen and the oxygen to the right hand side. Right? So obviously these are like, oxygen atoms are identical, but this is one oxygen, this is another oxygen. Clear? So we can have the double bond between this oxygen or this oxygen. Now which one is correct? Is there a specific correct one? Separate one, you can say, okay, this one is correct, this one is wrong, or both are correct? Both are correct. You can't say one is wrong, one is correct. Right? Because both are equally stable. You can see there is charge separation here also, -1 + 1, -1 + 1. Right? Now here in the tute, I actually reminded you about formal charges. Can you remember how formal charges are calculated? How are formal charges calculated? Valence electron number minus addition of number of bonds and the electrons in the lone pairs. Right? So you can do it that way, or a short method is you can remind yourselves for each and single atom the total number of valence electrons it should have. Now for example, oxygen's valence electron number is 6. Right? So we can see, is oxygen having its 6 electrons still intact? So for example, if you take this bond has one oxygen electron from this oxygen and another electron from this oxygen. Right? So this particular bond is made with one electron from this oxygen, one electron from this oxygen. And this bond is made with one electron from this oxygen, one electron from this oxygen. So therefore you can quickly count for each oxygen whether its valence electron number is fulfilled. So 1, 2, 3, 4. We know each of these bonds contain one electron from this oxygen. So 5, 6. Is that clear? Altogether 6 oxygens are complete now. Now if you go to this oxygen in the center, you have 1, 2, right? Each of these bonds contain one electron of that central oxygen. 1, 2, 3, 4, 5. It is missing one electron from the valence electron number. Is that clear? So therefore this has a positive sign. If you take a look at this oxygen, 1 2 3 4 5 6, and this bond also has an electron from this oxygen, so therefore 7 has one additional oxygen. Now we are supposed to calculate the formal charge based on the equation if they ever ask you a question, but at the exam, do you have enough time to write? Like imagine you are drawing a Lewis structure really fast for you to do MCQ or something like that. Do you have enough time to keep writing formal charge equation and then substitute those values for each and every single structure that you draw? No. So you have to have an idea about how to quickly get to answers. Is that clear? So the answer is that in this case. So now afterwards, after getting to that, we move on to what do you call it, another topic. I will show you, there's a lot more to learn about resonance structures. I'm just giving you a taste as to what resonance structures are. This is one such example. We have ozone, this format and this format. So that is going to be, this is structure 1, this is Lewis structure 2, that is stable. Both are correct. Both are correct. Right? Usually we draw this arrow as well. I'll come into that a little later. Take a subheading. Take a subheading. You can write additional details that might be helpful. Additional details that might be helpful when drawing Lewis structures. When drawing Lewis structures. Okay. Okay. So students, instead of writing Lewis structures, when drawing resonance structures, please write cut Lewis and write resonance when drawing resonance structures. Okay. Take a subheading, curvy arrows. Curvy arrows. We can write curvy arrows are often used, or just write curvy arrows are used. Curvy arrows are used to show electron transfer. To show electron transfer from a bond or a lone pair. From a bond or a lone pair. Can write the arrow should always start from a place where there are electrons, and point towards an atom, or between two atoms, I will explain these points further, right? For the time being, take it down, and then take this and write transfer of one electron, transfer of two electrons. Right. You took this down? Right. So students, although I didn't initially tell you, when you are usually drawing resonance structures, we normally indicate how the electrons are getting transferred when we are changing from one form to the other. We are starting with, imagine you drew this form, and then imagine you want to show what other forms can be drawn for the same structure. So we have to show how the electrons are shifting in order to get to different other structures. Now this is one structure, this is another structure. Starting from this structure, we can get to this structure. So we need to show how that happens. That is usually shown with the use of electron transfer curvy arrows. So what has happened here is, students, we have a double bond here, and this double bond is no longer there. That means the electrons that are present in this double bond has gotten transferred to this oxygen atom, right? So do you see now this oxygen atom has 3 lone pairs, because one bond that was present between this oxygen and this oxygen, those bond electrons, there were 2 electrons too, those electrons got transferred to this oxygen atom. Do you understand? Right? So let's say when that happens, what do you think will happen to this oxygen? Now this oxygen has earlier on 1, 2, 3, 4, 5, 6 bonds, 5, 6 valence electrons of its own. But once the transfer has taken place, do you see it gets a negative charge? Why would that happen? Because apart from getting his own electron back to itself, it is getting the electron that belong to this oxygen as well. Do you understand? Because this bond contains 1 electron from this oxygen and 1 electron from this oxygen. Both of them go into this oxygen. Is that clear? So it is like gaining an additional electron when we are transferring both the electrons to this atom. Is that clear? Imagine I have shared some certain amount of money, let's say 50 rupees with one of my friends, and he also has shared 50 rupees with me to start a small business. But you know what? He says, no, I don't want the money anymore, so you can take all of it. I take both the 50 rupees. Now, have I gained a total of 100 rupees back to myself, or have I gained only 50 bucks? I have only gained 50 because I have already invested 50 now earlier, and then he also gave 50. So now when I take both of them, I only have additional 50 rupees. Do you understand? So this bond in this bond there is electrons from this oxygen, both of them go to one oxygen atom, so it is only gaining one additional electron, right? One of the bond electron was already this oxygen's. Is that understood? Right. So when that is happening, another thing that has taken place is one of the lone pairs of this oxygen has gotten transferred between this oxygen and this oxygen, indicating this lone pair has turned into a bond electron pair. That lone pair has turned into a bond electron pair. So now the reason why I drew these arrows is because I want to show the electron transfer rules we were talking about. I told you this arrow with a full arrowhead represents transfer of 2 electrons. See, do you see here? This is a bond. This has 2 electrons. Both the electrons are transferred to this oxygen atom. Is that clear? So arrowhead is pointing towards what? An atom in this case. Right? Started with what? A bond. So we always have to connect the starting point, in the sense start of the arrow, to the place where the electrons are. Many of the times students fail to do that. Sometimes students draw it like this. You lose a mark for that. I'm not joking. They lose a mark if the arrow starting point is not connected to the place where the electrons are. So if the electrons that you want to show getting transferred are coming from the bond, the base of the arrow should be connected to the bond, like so. Is that understood? And in this case, electrons, this lone pair of electrons are getting transferred here. So you have to connect the lone pair and the arrows together. Since you can't connect the both electrons to the arrow base, we just connect one, that is fine, right? So the lone pair is getting transferred between the 2 oxygen atoms. So between the 2 oxygen atoms means there's going to be a bond formed between the 2. If the arrow is pointing towards only one atom, that means both the electrons are given to that atom. Between 2 atoms mean you are forming a bond between the 2. Is that clear? So arrow could point to one atom or between 2 atoms. If it is pointing towards one atom, that atom is getting both the electrons. If the arrow is pointing between 2 atoms, that means there is a bond formed between the 2 atoms. Is that understood? Clear? Right. So that is what is happening here, everyone. Okay? So this happens, you turn it into this. Now if you want to go back to this, what should happen is one of the bonds should get formed starting from this lone pair, and one of these bond pairs should break and be given to this. Is that clear? So under what you just wrote about additional details, can you please retake this with the arrows? Please draw the arrows in red if you possibly can, because it has to be very clear, especially in the initial stages, how the arrows are drawn. When you're done with it, let me know. Right. So now write another example. NO. So I want you to do that, right? I want you to attempt it. It's a simple example. Try to complete it. Example, not just NO, sorry, NO2 1 minus, it's better. It's better, it will be easier. Do this exercise. So I want you to draw the resonance structures. Draw resonance structures of NO2 1 minus. Now you can't be new to drawing Lewis structures, please. So therefore first draw one Lewis structure and then show the electron transfers and then show another resonance structure you can draw for this. Can I have it for a second? If you are done drawing it, please let me know, I will check. Please let me know. Now in the book, the one that we have is not complete, huh? So if you are looking at the book or tute, can I help you with the first Lewis structure then? Right, I see some of you are looking at the tute and trying to obtain an answer that way. So students, you can't remember, if I told you last week also, if you can't remember Lewis structures, you are going to be finding this part a bit difficult. So let me revise and tell you how to draw Lewis structure first of all, right? So anyone who is joining new also maybe will be able to understand what's going on. So to draw a Lewis structure, we have to take all of the valence electrons of each of the atoms into account. So Nitrogen has how many valence electrons? Valence electrons are the electrons that are found in the outermost energy level. So nitrogen has 5 outermost energy levels. So 5 outermost energy level electrons, right? Nitrogen has 5 valence electrons. Oxygen has how many outermost energy level electrons? 6. There are 2 oxygens. So therefore we have 12 valence electrons coming into this because of that. And this whole thing has a negative charge. A negative charge is usually obtained by gaining 1 electron. So we add an electron to this. So 5 plus 12 is 17, 17 plus 1 is 18 electrons. And we can count electron pairs. Electron pairs number would be 18 divided by 2, 9. So therefore altogether 9 electron pairs are there. And then we can count how many bonds are going to be there. So we have to remove the number of bonds here. So NO2 minus, so we have the nitrogen, which is the central atom, oxygens like this. So 2 bonds are used to connect the oxygen to nitrogen. So we reduce 2 here. We are left with 7. So we need to now represent 7 lone pairs around these outer atoms and then the central atom. So we are starting with outside atoms. Then only we move on to this. So we will add lone pairs until the octet is complete. So this bond contains 2 electrons, then another 2, another 2, another 2. Altogether 2, 4, 6, 8. Around oxygen 8 electrons are completed. Here also we have 2, 4, 6, 8. So now I have used altogether 6 lone pairs, but I have to put 7. So 6 is done. I have 1 more and I will include it here. Is that clear now? Understood? Now afterwards, students, we have to look at something called formal charges. Now formal charge number, can you remember how we found it? There is a formal charge equation. Formal charge is equal to, for a given atom, let's say oxygen, valence electron number, which is 6, minus number of bonds, just only 1 bond, added with total number of electrons in lone pairs. There are 3 lone pairs. Each lone pair has 2 electrons, so therefore 6 electrons. So what is the formal charge? 6 minus 7 minus 1, right? But we don't have to struggle that much, students. Like, now you guys are at a level where I can basically say count the total number of electrons that belong to only this oxygen. There are 6 here, and in this bond there's 1 here, right? You are now mature enough to understand that we have done these Lewis structures parts. I can basically say around oxygen there are 6 electrons here, and this bond contains 1 electron of oxygen. So therefore 7 electrons around there. So 7 electrons belong to oxygen in this case. That means oxygen is holding more than its valence electron number. 1 more, right? Valence electron number should be 6, but oxygen has 7 of its own electrons, meaning 1 additional electron is there. Is that clear? So again, this oxygen is also the same. Now nitrogen should have 5 electrons, valence electrons of its own. 1 valence electron here, second one is here, 2, 3. Sorry, 1, 2, 3, 4. Right? Altogether 4 valence electrons can be seen. 1 is missing. Is that clear? So that means nitrogen here is positive. Is it understood? So when drawing Lewis structures, we very clearly learned having this type of charge separation is unstable. We are trying to minimize the charge separation. So what do? We can convert. Now this is still not the correct Lewis structure. We are still getting to the Lewis structure. We will convert 1 into a bond pair here. Right? So we don't have to show those. We can directly show, okay, we converted 1 into a bond pair. Then the positive sign over here and the negative sign over here goes away. Right? I'm reminding you, why does the positive side on nitrogen go away? Because the lone pair was present on oxygen. When the lone pair became a bond pair, additional electron was gained by nitrogen. Earlier 2 electrons only belonged to oxygen. Now it's between oxygen and nitrogen. That means out of the 2 electrons, 1 belongs to nitrogen, 1 belongs to oxygen. It's like oxygen lost an electron, nitrogen gained an electron. Is that clear? Understood these parts? So this is something we have already done. So you get to this structure. Now if you are looking at the TUT doesn't have the lone pairs. Intentionally it was not given there, right? So if you are trying to correct the detail on the TUT itself, you can put the lone pairs and then get along with it. So the next structure, for you to obtain the next structure, what you can do is you can convert one of the lone pairs into bond pair between this oxygen and this nitrogen, and then one of the double bond electron pairs can be converted into a lone pair. That's it, students. That's it. So what do you get then? You get something like this. Sorry. Do you understand? Right? It's better to draw it with the correct shape, but I haven't drawn it here with the correct shape. If you're drawing it with the correct shape, it should be a bent angular shape like given in the TUT. Is that clear? Anyone who got to this answer the same way? Very good. Right? So you can even show how you can go back. Right? This can be formed. This can be formed starting with this, and we can form that again starting with this. So therefore you can show, if you want to get that back, you can do this. You go there. Is that clear? Not a very difficult thing to do. Copy it down, please. Did you get to that earlier? Huh? Right. Have you all completed the Lewis structures part at school? Still not? Okay. Or which lesson are you on? Which lesson are you on? You two are from same school. Which lesson are you on at school? You can't remember? Don't go to school. Unit 1, is it? Most probably Unit 1. Yeah? Which one? Sorry? Okay. But in your school? At least Unit 1 or Unit 2? 2. This part. Right, good. Right. So you all also Unit 2. Have you done resonance? No. Right. Okay. So now we'll start now. Did you understand this part? Is that clear? So now students, these are the key things that you need to take away from resonance structures. Pay attention. Resonance structures, you can't change the skeleton. Skeleton means the arrangement of atoms within the molecule you can't change. You can see oxygen, nitrogen, oxygen. You can't put oxygen in the middle and put nitrogen to a corner and say there's a new resonance structure. It is not, right? So you have to have this structure the same way, the basic skeleton the same way, and you can only change the electrons. You can shift electrons that are present as lone pairs and turn it into bond pairs, or bond pairs into lone pairs. That is all you can do, right? You can't, change where the atoms are. You can't take this atom and put it here and this atom and put it here. You can't do that. the skeleton, the structure should be the same, but the electrons can be transferred to get to new Lewis structure. And the stable Lewis structures you can draw for one molecule without changing its basic skeleton is referred to as resonance structures. And another key thing that I have given to you in the beginning of the note itself, when I was starting the class today, is the fact that the total number of lone pairs added with the total number of bond electron pairs, that means the total number of electron pairs in general, right? There are two types of electron pairs, no? Lone pairs and bond pairs. The total number of electron pairs can't change from one Lewis structure to the other. Is that clear? But the number of bond electron pairs can change, number of lone pairs can change, but the addition of the two can't change. Is that clear? So for example, one molecule can have 3 bonds and let's say 4 lone pairs. The other one can have, let's say, 2 bonds and 5 lone pairs. But altogether, the added value of the lone pairs and bond pairs should be the same. Right? 3 bonds and 4 lone pairs is 5 electron pairs. 2 bonds and 5 lone pairs is 7 electron pairs. Right? As an example, hypothetical example. So the number of bonds can change, number of lone pairs can change, but the total of bond and lone pairs added together, total electron pairs, can't change. Is that clear? Because no matter what we do, the total electron pairs come from this, right? Valence electron number of each element and then the charges that are there. So the total electron pair number can never change when you're talking about different types of Lewis structures. Now for example, here we have, in this case we have the same number of lone pairs and on both sides, but there are certain structures that we draw, even the lone pairs can change, bond pairs can change, but the total number of electron pairs never change. Here we have 1, 2, 3, 4, 5, 6 lone pairs, 1, 2, 3 bond pairs, altogether 9 electron pairs. Let's see here, 1, 2, 3, 4, 5, 6 lone pairs, 1, 2, 3 bond electron pairs. Altogether how many electron pairs? 9. Right, so from here to here the electron pair number has not changed. Is it understood now? Right, we'll do one final example and then after that I will move on to another part. Right, write down, draw the resonance structures for carbonate ion. Draw the resonance structures for the carbonate ion. CO3 1 minus, CO3 1 minus. Oh, sorry, CO3 not 1 minus, carbonate is not 1 minus, carbonate is 2 minus. Sorry about that. CO3 2 minus, not carbonate 1 minus, CO3 is 2 minus. Which school are you from? So to connect one nitrogen to oxygen, we need one bond. Another nitrogen, another oxygen to the same nitrogen, we need another bond. So those are the two electron pairs that are removed when it comes to bonds. Under bonds I have removed two, right? Those are the two electron pairs that got removed. Okay? Can I see? Okay. So now, yeah, good, not wrong. This is correct. But I know you get to this first. Don't need to show this though, right? When we are working out, you get to this, but don't show it. Directly draw the, you convert it and draw. You can draw it as a sketch somewhere, and then finally draw the correct structure, because this is not something that should be there alongside the resonance structures. And if you pay attention, there is another resonance structure. You are correct. The ones that you have drawn are correct, but there's one more. Lewis structures matakada. Try to remember, and if you need any help, let me know. So we have carbonate, right? I will now start. It's enough time. So we have carbon. Carbon has 4 valence electrons. Oxygen has 6. But there are 3 oxygens. So 3 into 6 is 18. The total negative charge is 2. So we have 2 minus charge. That means, now when an ion has negative charge, we have gained electrons. The magnitude of the negative charge tells us how many electrons we have gained. 2 minus means how many electrons? 2 electrons have been gained. So 20 plus 4, 24 electrons. Now electron pair number would be, electron pairs would be half of this. 24 divided by 2. 12. Then we draw the main skeleton. So we have carbon connected to oxygens. I utilize 3 electron pairs there. 1 electron pair, 2nd electron pair, 3rd electron pair. So that means I have already represented 3 electron pairs. I can subtract that. I normally write here bonds. Right, these are bond electron pairs that we subtract. So then we are left with the number of lone pairs I need to indicate there. So number of lone pairs I need to show in the initial Lewis structure is 9. So I need to put electrons to the outer atoms until the outer atoms octet is complete. So that means around the outer atoms 8 electrons should be complete. That is called the octet. So the 2 bond electron pairs are there. Right, 1 bond means 2 electrons, so we need to add 6 more to complete the 8. So now the 8 around oxygen is complete. Here also the same, each of these oxygens are similar. 8 is complete. 8 is complete. Is that clear? Now you can take a look at the formal charges. I have told you when we were doing Lewis structures, whenever oxygen has a bond and 3 lone pairs, we don't have to even calculate. And I like for me also it gets boring to repeat the same thing a million times. What is the oxygen's formal charge? Here, minus, right? Why? 6 electrons and 1 electron from this bond, 7 electrons of oxygen. Oxygen should have only 6 valence electrons. But according to this structure, oxygen has 7 valence electrons. Right? Oxygen should have only 6 valence electrons. According to this structure, oxygen has 7 valence electrons. So therefore, this should be 1 minus. That means oxygen has gained additional electron. So each of these oxygens are the same. It has gained 1 additional electron. Is that clear? Now students, carbon has how many? 1, 2, 3 bonds. Each of these bonds contain 1 valence electron of carbon. Right? So how many valence electrons of carbon can be seen here? Only 3. Right? How many valence electrons are there for carbon? 4. 1 missing here. So therefore, we have a positive charge on carbon because the electron is missing. Electron is lost. So therefore, students, like everywhere formal charges, minus, 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 plus, every atom has a formal charge, very unstable. This is not a correct Lewis structure. This Lewis structure is wrong. It is not correct. So many formal charges is not stable. So what do? To balance it out, we have learned to convert a lone pair into a bond pair. That was done to draw the correct Lewis structure. We are still drawing the Lewis structures. We are not even close to resonance structures yet. We are drawing Lewis structures. So we will convert one lone pair into a bond pair. When you do that, this is the situation. This oxygen has 1, 2, 3, 4, 5, 6 electrons as valence electrons, so it is neutral. This carbon has 1, 2, 3, 4 valence electrons. It is also neutral. Right? 4 bonds around carbon means each bond contains 1 electron of carbon. So therefore altogether 4 bonds means 4 valence electrons are represented around carbon. Is that clear? Now these two are negative. You can't remove those negative charges because this ion is anyway 2 minus. You have to have 2 minus, no? Right? So students, if you want to draw Lewis structures, not Lewis, resonance structures for this. Now this is the correct Lewis structure, okay? We are starting with this correct Lewis structure. If you want to draw resonance structures for this, we need to keep shifting bonds here and there. Now let me give you a small hint. This carbon is connected to 3 of the same atom. But between carbon and oxygen, there is a double bond. What we need to do is, we need to keep shifting this double bond from here to here and then to here. Is that clear? Double bond could be here, here or here, 3 places. So you can draw 3 resonance structures. And that can be shown this way. You can say this bond, so this lone pair comes here. So then there's a double bond there. And this double bond breaks and goes here. Okay. Now why can't we have 2 double bonds on carbon? Why can't we have 2 double bonds on carbon? Carbon is a period 2 element. It can't hold more than 8 electrons around it. Period 3, period 4 elements can, but carbon, nitrogen, all those period 2 elements can't. So here we have carbon connected to an oxygen with 3 lone pairs. This is one resonance structure. The other one would be this lone pair going up, and so this bond pair going up, and the lone pair on this oxygen comes to a bond. So it turns into something like this. Is that clear? Do you understand now? Right? If you want to go back to this, you can say this happens. Right? So you can go back to this. Anyway, is that understood? Now when you are learning resonance structures, we have to show the electron transfers very clearly. In certain questions also they very specifically ask for the electron transfers. But later down the line, they might ask you to, like in certain questions, not use it, but as a rule or as a practice, always show the electron transfers. It will be easier for you. Okay. Some of you can draw it without, like some of you will come to the level where you don't need the electron transfer to be shown. You know the structures, but it's always better to show the electron transfers so that you don't make any mistakes, as well as you won't lose any marks. Now, are you clear with the resonance structures? Right. So, all of you have taken it down, right? So, these resonance structures, do you see? They are equal to one another. They are very similar to one another, right? So, these are called equivalent resonance structures. They are called equivalent resonance structures. That means they look pretty much the same. Only difference is the place of the double bond has kept on shifting, like from here to there, right? Like it's going to keep on shifting between similar atoms. Pretty similar, but only difference is they keep shifting. But there are other resonance structures that are somewhat non-equivalent. So turn to page number 28, right? Page number 28. Turn to page number 28, please. Now those aren't very equivalent resonance structures. You can say they are pretty similar, but one is unstable. One is unstable than the other. Can you tell me which one is unstable? Can you tell me which one is unstable? The A structure is unstable. Why is it unstable, students? Because an electronegative element like chlorine has a positive charge on it, and plus you can have that same molecule without any charge separation as well, without any formal charges. So at that point, one is very stable Lewis structure, or the other one is very unstable Lewis structure. Then we say they are not equal to one another. We say they are not equal. So we say non-equivalent resonance structures. One is unstable, the other one is stable. Right? Sometimes in certain cases both are somewhat stable, but stability wise they have different stabilities. One is very stable, the other one is moderately stable. Now in this case, of course, it is unstable. One is stable, the other one is unstable. So they are non-equivalent. But over here you can see each of these have carbons that are not having a formal charge. Each of these have two oxygens with -1 formal charge, right? And one oxygen with double bond. Basically the same thing, right? Everyone has the same stability and the same structures, same everything. Only difference is the position of the double bond has shifted. These guys are equivalent resonance structures. Is that clear? Right? So you need to hear these words. We will dive further into it when we are talking a bit more in detail about what do you call it, resonance, something called resonance hybrid. Page number 29. I'll take this for a second. Page number 29. So when drawing resonance structures, or when drawing Lewis structures in general, these are the main rules that you need to adhere by. The first one is structures that can be drawn with a minimal amount of formal charges on them tend to be more stable. Is that clear? Now for example, if you take a structure where there is formal charges on each and every atom, not stable. You need to do something to make it stable. Right. So structure with less number of formal charges on the molecule is good. The other thing is having the same sign formal charge on bonded atoms like this. For example, these two are bonded together. So these kind of bonded atoms, they can't have the same formal charge. Plus plus, O plus minus, sorry, minus minus, not plus minus. These are same charge on adjacent atoms. Adjacent means they are bonded together and close by, right? Those kind of formal charges, separation is bad, unstable, because similar charges repel. However, now situation like earlier, can you remember when it comes to talking about ozone? When it comes to talking about ozone, we had this structure, right? Ozone, we had this structure. So this is positive, this is negative. Now that was okay. Adjacent atoms with opposite charges is fine. When I say adjacent atom, they should have a bond between them, okay? And these two are not adjacent. They are not bonded together, no? Okay? So these two are adjacent. So when it comes to adjacent atom having opposite charges, it is okay. But having the same charge, not fine. Is that clear? And when it comes to resonance structures, if you are drawing resonance structures like this, imagine you have highly electronegative element like nitrogen having a positive charge and this is having a negative charge. If you have a positive charge on this, it is unstable. Carbon can have a negative charge, that's a different story, but like very electronegative element can't have a positive charge. Having so would make it little bit unstable. Is that clear? So the more negative elements should be given the negative charge. Less electronegative elements should be given a positive charge whenever possible. Is it understood? Clear? Those are the simple rules, students. We discussed these rules little bit in detail when it comes to Lewis structures as well. When you're drawing Lewis structures, the Lewis structures will become more stable if you follow these same rules. Understood now? Okay. Right. So I will, before we go for a break, I will talk about the most important part of these resonance structures and then draw you a new type of molecule and we'll close it there. I will give you some work as well. So now, if you take a look at, I'll keep this molecule here. If you take a look at this molecule, and if you analyze this molecule using the current equipment we have, you will observe a bit of a contradicting thing to what we observe here. Now, according to the molecules we have drawn, a carbonate ion, or according to the structures we have drawn, a carbonate ion has the following bonds. It has one carbon oxygen double bond. Now when a double bond is formed, the bond length is smaller, right? We discussed this last week, right? Bond strength and bond length. I gave you sentence. If I have given you, do this, did I give you a sentence about bond length and bond strength? There's just one sentence, that's it. We discussed double bonds and triple bonds. Okay, if I haven't given you that sentence, I can give it to you now. Right, we discussed double and triple bonds, right? Yeah? So now pay attention. So it's okay. So I will discuss it here. Now, since I haven't given you the bond length and bond strength part. So we will take a note down later on, not now itself. So if you take a carbon-carbon single bond, single bonds are obviously weaker than double bonds. Triple bonds are stronger than double bonds also. That is common sense. More the bonds, the stronger it is. But apart from that, we also observe another thing, that is carbon-carbon double bonds tend to be shorter than single bonds. Why? Because there is a direct overlap of orbitals when it comes to single bond. Now when it comes to a double bond, apart from the direct overlap, p orbitals laterally overlap also. That means the atoms have to come a little bit closer to laterally overlap. In a triple bond you have two pi bonds. That means two lateral overlaps. That means they come even closer. Is it understood? Now think of, forget about bonds, think of rubber bands. Imagine you have two sticks that are separated here. You put a rubber band here and keep them together. You put another one. Then now what happens? They are somewhat close together now. You put another one, the third one. They become even closer. Is that clear? So the more the bonding, the atoms become closer and closer together. Is that understood? So the bond length in carbon-carbon bonds is longer than carbon-carbon double bonds. Carbon-carbon single bonds are longer than double bonds. And carbon-carbon triple bonds. Now although I take carbon, this is true for any bonding. So single bonds are longest, then double bonds are shorter than single bonds, and triple bonds are even shorter than double bonds. Is that clear? Right. So students, the reason why I am bringing this up is because according to the structure we have drawn, we have one carbon-carbon double bond and two carbon-oxygen single bonds. Sorry, one carbon-oxygen double bond and carbon-oxygen single bond. So this particular bond is shorter. And this one is longer. Right? So now we have equipment, students, that will allow us to measure the length of bonds. There are equipment where we can measure the length of the bond. So when we put carbonate ions and when we are analyzing carbonate ions with the use of those kind of equipment, we observe that carbon oxygen when it comes to the carbonate molecule, we observe carbon oxygen single bond and double bonds, those lengths are not seen in carbonate molecule, right? The machine says you don't have two different types of bond lengths. We don't have this bond length also, we don't have this bond length also. Machine says there is some sort of bond that is in between a carbon bond, a single bond and a double bond. Bit weird, right? Machine says you don't have carbon oxygen double, because we know the lengths. We have analyzed millions of molecules now, not millions, thousands of molecules now, right? So now we know the bond length of carbon oxygen double bond. Machine says no, that bond length is not there. And we know the carbon oxygen single bond. Machine says no, that bond length is also not there. Machine says there is a bond length between a single bond length and a double bond length. So the bond length value is between this bond length and this bond length. Is that clear? So if I draw that diagram, it's like this. If I draw it in proportion, let's say carbon oxygen double bond is having this specific length and obviously carbon oxygen single bond should be longer, right? Like that. So when we analyze this molecule, we expect this bond length to be found in the machine and this bond length to be found in the machine as well. But the machine says no, those bonds are not practically seen. What we have is something in between. What we have is something in between. You understand? And plus we don't have two different types of bonds. Like, you know, here we have two different types now, single bonds and double bonds. According to the data obtained from the machines, it says no two different types of bonds. There's only one type of bond. So now that means the structures we drew over here, right, these resonance structures are not actually present in the real molecule. In the real molecule, these resonance structures are not there. Instead, the real molecule has a completely different structure. Right? What is it? It is a mix of these three. We say a hybrid of these three. Is that clear? If you put all of them together, the hybrid version of these three structures is what we observe. Is that understood? So according to that, what you have is a structure like this, and we call those resonance hybrids. So this is called resonance structures, and what we have in real situation is something like this. Right? Okay? So you can see this double bond is spread throughout three bonds. So we have one bond, and this is 1/3 of a double bond. Is that clear? So that is why the bond length came between a double bond and a single bond. The bond length between these oxygens are not exactly 1.5, it's like 1.33, because this double bond is going to be shifted between these three places. So a double bond is present between three different places, spread out. So here what I have indicated through a dotted line is 1/3 of a bond. We obviously have a correct single bond, but the rest is 1/3 of a bond. So this is not a double bond, this is not a single bond, it's like 1.33 of a bond. Is that clear? Somewhere in between. Right? You are not going to be asked like, you know, it is 1.33 of a bond, no. Right? So there's something called bond order, but we don't necessarily have to talk about it now itself. Is that clear? So, and this negative charge. There are two negative charges that keep on shifting between three atoms. The total number of charge is 2 minus, but it gets shifted between three atoms. So therefore we write negative charge 2 divided by 3. 2 minus divided by 3. Is that clear? If you add all of these negative charges together, the overall charge is going to be what? Minus 2. Is that clear? Is it understood? Right? So yeah, this is referred to as resonance hybrid, often drawn like this as well. Often drawn like this as well. Okay? Right? So this is why we don't see two different bond lengths according to experimental data. We don't see when it comes to carbonate ion, there are no two different bond lengths. You only have one type of bond. right? That is a bond that is between a single and a double bond. Clear? And this pi bonding is like 1/3 of a pi bond. Is that clear? Right. So under new heading, write resonance hybrid. Resonance hybrid. I will give you a small note on it. Please write. The real structure of a given molecule or ion, is not indicated by any of the resonance structures. Instead, the real structure is thought to be a hybrid of the stable resonance structures drawn. Hybrid of the stable resonance structures drawn. Right? If the resonance structures, as a separate point, please write. If the resonance structures for a given molecule or ion happens to be equivalent resonance structures, each of those contribute equally to produce the resonance hybrid. Each of those contribute equally to produce the resonance hybrid. So let me explain what I mean by that. So do you see this is the resonance hybrid, right? This is the resonance hybrid. We can draw it like this as well. So the resonance hybrid, got formed due to these resonance structures. But all of these resonance structures are equal or equivalent resonance structures. So therefore, they all had an equal contribution to this resonance structure. They all contributed equally. Now you can't say this particular resonance structure looks mainly like this one and not like the rest. Can we say that? We can't say that, no? Because this looks like this as well as this as well as this. And there was an equal contribution to this resonance structure. But when it comes to certain resonance structures, you will come across later down the line, and at that point I will show you. I don't want to complicate it too much in the start itself. There are certain resonance structures where one structure is stable, the other one is moderately stable, and another one is unstable. You can draw resonance structures. You are the one who's drawing it, no? Right? So the resonance hybrid that you have drawn is mostly going to be taking contribution from the most stable structure. So therefore it's going to resemble more like the most stable structure. Is that clear? So therefore the contribution coming from the most stable structure is much greater than the contribution coming from the less stable structures. Is that clear? So therefore when it comes to non-equivalent types of resonance structures, their contribution is also going to differ. So since at your stage it's very difficult to figure out which is contributing more, which is contributing less, the questions that revolve around non-equivalent resonance structures in your level is almost none. Now you don't get many questions about, okay, tell me the contribution from this structure. Right? There won't be any question asking for calculations of the contribution of one particular structure. But you should be able to comment saying this structure is more stable than the other. So therefore this structure contributes more towards the resonance hybrid than the other one. Imagine one is stable, the other one is not stable. So the stable one will be contributing more towards the resonance hybrid than the unstable one. Right? So you should be able to comment on it. Is that clear? You understand? But you are not going to be asked anything beyond that. You will ask based on those things which resonance structure we do not, sometimes the most unstable ones you don't even consider when drawing the resonance hybrid. You have to draw the resonance hybrid. So imagine these two are stable and you have drawn some completely unstable one here. So you don't even consider that when drawing the resonance hybrid. Is that clear? So you need to develop a sense about this. Last sentence over here. Under that, please write. When it comes to non-equivalent resonance structures, the most stable resonance structures has a greater contribution towards the resonance hybrid compared to less stable resonance structures. Compared to less stable resonance structures. Now the questions I have given you here, the ones that I discussed, are quite easy ones, right? So I want you to get your head in the theory parts first, and then later on we will move on to bit difficult resonance structures and exam questions. So towards the end of this unit we will be talking about mainly past papers. So we'll take one whole class and we'll discuss past paper questions coming from these parts. And we will now quickly discuss did you take this down? Under that? Right, take this down. Normally when you are drawing a resonance hybrid, we have to have the resonance structures nearby, right? Otherwise you can't figure out how those two are related. So please take both of them down, or else you can just take a look at the TUT has this. Complete the diagrams in the TUT, that is also fine. Diagrams TUT are not completed, I left it for you to complete. So diagrams in the TUT, complete it in the TUT if you want. After the break I'll give you more instructions on how to draw the resonance hybrids. Are we done? Right. We'll take a small break. Okay. And any questions? Okay.
What's the concept of one odd?
We talk about the total number of bonds between the two atoms. So there we talk about here whether we have one bond, two bonds, or three bonds between the two atoms. Right. So in this case, it will be not one, not two, somewhere in between, like 1 and 1/3. 1.33 would be the case. Okay. Right, everyone. Shall we take a small break? Now it's 4:45. We'll take a small break and we'll start the class again at 5. Are these parts clear to you? It's cool. Okay. Right, everyone is here now, so we'll start. Okay. Write a new question there. Write a new question. Draw the resonance hybrids. Draw the resonance hybrids of the following molecules and ions. The following molecules and ions. First one, ozone. We have already done it, so it's quite easy. First one is ozone. Second one is, let's say, nitrate. NO3, 1 minus. Third one is sulfate. Can you quickly do these three? So since we have already done ozone, I will quickly recap what we need to do. When a question like this is given to you, you should show the resonance structures and then the resonance hybrid. So the resonance structures are these. There's 2 lone pairs on each, this oxygen, and this oxygen has 3 lone pairs, and this was one of the Lewis structures you can draw. And then due to electron transfer, you get to this resonance structure, minus here and the plus is here on this oxygen. These are the only 2 resonance structures you can draw. They are all equally stable, they are pretty similar to one another. So therefore these are equivalent resonance structures. And the resonance hybrid is going to be having, now between each oxygen there's at least 1 bond, right? That's what we do. We see the things that are not changing. We draw the things that are not changing first. Between each of the oxygens there's at least 1 bond. We draw those. Is that clear? Those are common to both. No? We draw only the common ones. We draw only the common ones first. This one has a double bond, this one has a single bond. A single bond, double bond. So we are not going to touch them yet. We draw the common stuff. This oxygen has a lone pair. Again, this oxygen also has a lone pair. And on both of those oxygens, very clearly we have a positive charge. Does that one have one and this one not have one? No, right? Both have the positive charge. So therefore, without any hesitation, put the positive charge. Okay? This one has 2 lone pairs, this one has 3. But at least 2 is there on each. No? So for the time being, we'll include 2. Right? This one has 3, this one has 2. Again, minimum number is 2. 2 is there. Right? And then we write the rest of the parts. So now everything common is written here. So now when you are moving forward, you take a look at the double bond, single bond nature. Here this is having a double bond, and this double bond is shifted between 2 different places. So therefore, we have to have roughly about half of a bond on each of these places. Right? So the bond order, the number of bonds between these 2 oxygen atoms is 1.5. Is that clear? The total number of bonds is 3. You can see 1, 2, 3. So this, between this oxygen and this oxygen and this oxygen and this oxygen, is having the same number of bonds. So the bond order would be around 1.3. Is that clear? Is it understood? So 1.5 here, 1.5 here, together 1.5 multiplied by 2 is 3 bonds. Is that clear? Or else you can think of it this way. A single bond between oxygen and oxygen is distributed among 2 places. So single double bond or single pi bond is distributed among 2 different places. So pi bond divided by 2. 1 sigma bond and half of a pi bond is there. 1 sigma bond and half of a pi bond. 1 sigma bond and half of a pi bond. Is that clear? Do you understand? So bond lengthwise, this is longer than a double bond, shorter than a single bond. Anyway, after that you can see this negative charge. So that negative charge keeps shifting between this oxygen and this oxygen, or otherwise it is shifting between these two oxygens. So each oxygen has half of a negative charge, half of a negative charge. So that is a resonance hybrid. Usually the charge separation, if you want, you can show it like this as well. There's no overall charge. There's no overall charge in this case, right? Within brackets, if you put the charge, what happens? Outside the bracket, there should be no overall charge because these two together is -1. There's a +1 here. Zero charge outside the bracket. Is that clear? Right. So that is how the resonance structures are drawn, students. That is how the resonance structures are drawn, and then the resonance hybrid is drawn. Can you move on to nitrate and sulfate ions? Nitrate and sulfate. Draw the resonance structures, then the resonance hybrid. Marker. If you need any help, let me know. Now, I'll tell the class, enter class. Right, everyone. So, keep in mind, nitrogen can't have more than 4 bonds. Why not? Because nitrogen is in the period 2. Period 2 elements can't have over 8 electrons around them. Okay? So if you are drawing the nitrogen and nitrogen has around 5 bonds, that is wrong. Can I quickly, because I saw how you are answering, let me quickly get that done. I have given you enough time for nitrogen. So nitrate ion, NO3 1 minus. If you are drawing the Lewis structure, nitrogen has 5 electrons, oxygen brings 6, so therefore 18 electrons. 1 minus charge brings 1 electron. Altogether 19 plus 5 is going to be 24 electrons. Electron pair number would be 12. So we have nitrogen connected to 3 oxygens, right? So therefore 3 bonds are used. So bonds would be 3. So therefore I need to represent 9 lone pairs. So 9 is the number of lone pairs. So I know I need to complete octet around oxygen. So then I put like this. So now the octet is completed. But if you take a look at the formal charges, each oxygen is 1 minus in charge. Nitrogen should have 5 electrons around it. However, there's only 1, 2 and 3 electrons. So therefore 2 negative charge is 2 positive charge is found around nitrogen. So you would have tried to minimize this nitrogen charge by converting one of the lone pairs into a bond pair of oxygen. So one of the oxygen bond pairs you would have converted into a lone pair. Sorry, lone pair into a bond pair. So then you have the electron of oxygen turning into bonds. So therefore oxygen is losing electrons, it becomes neutral. Nitrogen is gaining electrons, so it will go from plus 2 to plus 1. Now some of you have converted another lone pair into a bond pair, which you can't do. Nitrogen is a second period element. Second period elements have only 2 energy levels. In the second energy level, it can hold only 8 electrons, right? So that means it can't exceed. Now each of these bond electrons, where are they held? It is present in nitrogen as well as, like this bond electron is present in oxygen as well as nitrogen. So nitrogen has 4 bonds. So 4 bond electrons are going to be found in nitrogen. Altogether total of 8 electrons. So that means nitrogen's outermost energy level is fully packed now, filled. It can't hold any more additional electrons. So you can't convert another lone pair into a bond pair. If you do that, it's wrong. So nitrogen has a double bond between oxygen and 2 single bonds between 2 other oxygens. So now you can convert between the two. You can convert between the two by transferring electrons. You can have this lone pair turning into a bond pair and this bond pair turning into a lone pair. So you have something like this, minus and bond electron pairs and lone pairs are written here, minus. Apart from that, you can again have another electron transfer. These electrons can go here and this can form a double bond. Like this. So these are the stable resonance structures of nitrate ion. Stable resonance structures of the nitrate ion. These are resonance structures. Resonance structures are usually drawn with these, like, two-headed arrows, because we assume now this resonance structures concept and resonance hybrid concept is an imaginary concept. We develop it to understand the bond lengths of a molecule or ion, right? All of these things I did. Molecules come and tell us, you know what, I have something called resonance structures. Then they get mixed together, right? And then we form something called resonance hybrid, right? Was there anyone who saw a molecule talking to them and say these things? No, right? And did we see molecules? Are we able to visualize molecules? Are we able to see atoms? Are we able to see these bond electron transitions? Can we see them yet? We currently don't have the technology to see atoms properly, right? We can make predictions. Actually, very recently we visualized an atom, but that is also with the greatest amount of difficulty, right? So we don't see these things. We assume this is what is happening because according to the experimental data about bond lengths, we realize although the Lewis structure we draw it like this, according to the experimental data, nitrogen oxygen bonds are all the same, equivalent bonds, same length, right? What does that mean? The Lewis structures we draw are wrong. So then we introduce a new concept called resonance structures, and based on resonance structures we develop something called resonance hybrid. All of these are imaginary concepts we use to explain the bond length. We use to explain the real situation of the molecule. Is that clear? So resonance structure is not a no real thing. We use it to explain and understand the actual scenario of a molecule. None of us have seen these things. Is that clear? If you ever see an atom, let me know. Call me up. Say, sir, I saw an atom today. It's pretty beautiful. So some of you might, right? Maybe in my deathbed you will see. Because at that point the technology will be advanced enough for us to sometimes say, who knows. But the thing is, students, in 1990s, like when I was about 10-15, I was thinking by now we will have flying cars and stuff. Like now it's 2024, right? Nothing much has changed. Every new year new iPhone comes out or Samsung comes out, that's about it, right? That's the newest thing, that's it. So yeah, but I hope you will see, you live to see the day where you actually properly see atoms, where we have the technology to see atoms, right? So now the resonance hybrid. So the resonance hybrid, students, is consisting of the basic thing that is common to all three. Common to all three resonance structures is these bonds, and on nitrogen there's always a positive charge, right? That is common. And on each of the oxygens we can see there is at least 2 electrons, 2 lone pairs, that is common. And apart from that, nothing else is common. So the other thing is one pi bond is distributed among 1, 2, 3 different bonds. It is here once, it is in the second bond, and then the third one. So therefore it is getting distributed among 3 of these oxygen nitrogen bonds. So we say the bond order here is 1.3. The reason why we say 1.3 here is there's one full sigma bond and there's no one full pi bond. Instead of that, a single pi bond is distributed among 1, 2, 3 places, right? So single pi bond is distributed among 1, 2 and 3 places. So we say 1/3 pi bond. right? 1 sigma bond and 1 over 3 pi bond. You can say 1.3 because when you divide 1 over 3 you get to 0.33, right? So therefore we can say 1.33 bond order is there. Bond order is the total number of bonds between the two atoms. Total number of bonds between the two atoms is, in this case, 1.33. Is it understood? Right. So students, do you see each of these bonds are now equivalent, in the sense the same length? This one has the same length as this, right? And each of these resonance structures were equivalent resonance structures. I'll give you an example for non-equivalent one before we finish up today. So this is the answer. Is that clear? So the charge, I forgot the charge. Charge would be, there are two negative charges that keep shifting between three atoms. Two negative charges, but it keeps shifting between three atoms. It keeps shifting between three atoms. So therefore on each atom we have minus 2 divided by 3, minus 2 divided by 3, minus 2 divided by 3 charge. Is that clear? Draw both of these, or you can draw it this way. Or you can draw it this way. The overall charge can be written outside. For the nitrate ion, the overall charge is minus 1. Overall charge is minus 1. It is written outside. So you can draw it like this or that. Start with the sulfate ion, please. Anyone done with the sulfate ion? Sulfate ion has a few, no? Yeah, it can shift between few different places, correct? Very good. So you are getting correct. Good. So when it comes to writing charge outside the bracket, it should be 2 minus. 2 first, minus later. Anyone who has done the sulfate ion? I added you to the group, right? You sent me a message, I added you to the group. Yesterday. Some time ago, right? Sorry, yes. Sulfate has 2 double bonds, huh?
So how do you assign value to this resonance?
How do you assign?
A value to this.
Bond order.
Yeah.
So there's clearly a single bond between nitrogen and oxygen, right? And do you see this double bond is what keeps shifting between these three places?
Yeah.
That means the second bond here has gotten spread among 1, 2, 3 places, right? So then one bond is spreading among 3 places. So that is going to be 1/3 of a bond at each place. Do you understand? So each place has 1 bond and 1/3 of a bond. So therefore 1 bond plus 1/3 of a bond is 1.33 bonds. Right? 1/3 is how much? 1.33. Okay. Sulfate, can I see sulfate? All of these are dashed lines, right? Is this a full bond? Dash, right? Correct. Good. Sorry.
This is supposed to draw every possible outcome, so at least give one chance to one atom.
Normally we have to draw every possible outcome. No, it's okay. You have to draw, yeah, there's going to be a few, right? But and plus, in this case, if you have drawn, you have to draw 6, but normally you don't get that kind of question. Mostly about 4 or 5 resonance structures is max. This one has about, it keeps not only double bonds, but you can shift this here and then here while keeping this still, and then you can shift those here like separate places. So yeah, we have a few. Right? You got to that answer? Right, correct. We normally write the charge later after the number. When it comes to half values only, we write the charge first. Sulfur has 2 double bonds. You can convert one of those also into one pair.
So this is only work for nitrogen where you can't convey double bond.
Not only for nitrogen. Now period 2 elements are there. So starting from sodium all the way to argon, all those elements, right? Not sodium. Starting from lithium, period 2 elements: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. They can only have 8 electrons in the outermost energy level, right? But period 3 can have 18, period 4 can have 32, so on and so forth. It increases. So like any element in period 2 can't exceed 8 electrons in the outermost energy level. That's why they can't have more than 4 bonds. Okay? Number of bonds between considered 2 atoms. N of the resonance structure. N of the resonance structure. Number of bonds between the considered 2 atoms. Okay. And the amount of resonance structures. So then you add all of these together based on the resonance structures and then divide by that. Yeah, you can get to that, but you can get to it in a more logical way also. Now for example, here you can see this pi bond is distributed among 3 different locations. So that means it gets spread in 3. So not in a single place you don't have a single pi bond. You have 1/3 of a pi bond. So when you draw it like this, it is very clear. This is 1/3 of a pi bond. This is a single sigma bond. So 1 and 1/3 added together. 1/3 added together is 1.33. Is that clear? But this is okay. I think number of, can we see, if you, let's say we want to see the bond order here, so then 1 2 3 4, right? 4 divided by 3, 4 divided by 3, you are getting to the answer 1.13, 1.33. Do you understand? So they are asking you to check all the bonds between these 2 atoms. 1 here, 2 here, 1 here, altogether 4, right? And the resonance structure number is 3. So 4 divided by 3.
One oxygen. This oxygen has this time is 1, and this oxygen has this time 2, and this time this 1 and
Yeah.
storage.
Yes. So when it comes to bond order, we talk about specific bonds now.
Yes.
Right. Okay, everyone. So pay attention. When it comes to sulfate, I will not draw the entire set of resonance structures because it will take a lot of time. But if you take sulfate ion has this Lewis structure. This is the most stable Lewis structure for sulfate. This is a sulfate ion. Is that clear? So you can keep on shifting electron pairs. So then the double bond will shift from here again to here, and sometimes adjacent atoms can have double bonds. So you can show the shifts. I think about 6 Lewis structures can be drawn. So based on those are all equivalent Lewis structures. Based on those, the resonance hybrid that you obtain happens to be, now I have seen all of your answers. Most of you have gotten to this answer, which is good. The resonance hybrid would be something like this. right? And then there were two negative charges that keep getting, like, shifted among these four oxygen atoms. These two negative charges, they keep getting shifted among these four oxygen atoms. So therefore the total charge on each of these atoms could be 2 divided by 4 minus, in other words, 1 over 2 minus, or minus 1 over 2, minus 1 over 2, minus 1 over 2, minus 1 over 2. So at that point, this is the resonance structure. If you want it to be drawn without showing formal charges on individual atoms, you can do so as well. Like this. Is that understood? Right. So these are equivalent resonance structures. Most of the time when you are asked to draw a resonance hybrid at your level, it would be equivalent resonance structures. If they give you non-equivalent resonance structures, they wouldn't ask you to draw a resonance hybrid. Why? Because you don't know the contribution. You don't know which one contributes how much. Like, you can only say it contributes more. So because of that, what kind of structure is going to be produced, you can't definitively say, right? Sometimes it's very obvious when you, like, let's say if something is extremely unstable, you leave it out. Then at that point, you can say out of the three structures, one is given now off, so the other two will contribute to the resonance structure. But we need to know what this thing is all about. So we'll take a small subheading and write a small example question under the, we'll take a question, right? We'll take a question. Write down first question, or first part of the question. Draw the Lewis structure. Draw the Lewis structure of nitrous oxide. The formula is N2O. Draw the Lewis structure of nitrous oxide within brackets N2O. That's the first part. Draw it. Draw the Lewis structure first. I'll give you the second part later. Sorry, can I have it for a second? Have all of you drawn that? I'll quickly do that question, otherwise I can't move forward. for the A part of the question that I gave you, N2O, nitrogen is having 5 outer electrons, that there are 2 nitrogens, so therefore this is going to be 10 electrons. Oxygen is going to be 6 electrons in the valence shell, so therefore 16 electrons. Electron pair number would be 8 electron pairs. Now we have to pick a central atom. Now I know some of you did this, right? If you have done that, it is wrong. Now just because it looks like there is only one of them, we put it in the middle, you can't do that. You have to still remember the rules when picking the central atom. What are the rules? The central atom should be able to make more than one bond. Rule number 1. The other one is central atom should have a lower electronegativity. Out of the 2, nitrogen and oxygen has 3.5 electronegativity, nitrogen has 3.0. Which one is more electronegative? Oxygen. Can we put it in the middle? No. Right? So the central atom has to be a nitrogen atom. To that you have a oxygen connected. And the other nitrogen atom also connected to the central nitrogen atom. So there's only one central atom, the other 2 are connected to that. So when you're choosing the central atom, keep in mind the central atom can't be more electronegative than the other atoms. Central atom is the least electronegative compared to other atoms, right? So the other requirement also have to be kept in mind. Central atom should be able to make more than one bond, or multiple bonds we say. So this is wrong. So here we have 2 bonds. That means we have to subtract the bond electrons. We have 6 here. So then therefore we can distribute the lone pairs here now. 1, 2, 3. 1, 2, 3. Right, started with the more electronegative element and then moved on to the less electronegative element. We don't have any remaining to give the central atom, right? So now this is 1 minus charge. Now let's count the valence electron number around nitrogen. 2, 4, 6, and one of these bond electrons is nitrogens. So 2, 4, 6 and 1 is 7. So therefore there are 7 valence electrons. Nitrogen can have only 5. Now it has 7, meaning this has taken 2 additional electrons. So therefore nitrogen is minus 2 in charge. And this nitrogen is plus 3 in charge, right? Because it has only 2 valence electrons, nitrogen should have 5, missing 3. So therefore plus 3. So you convert these lone pairs into bond electron pairs and then you get to the answer. So if you convert these 2, you get to a bit of a stable Lewis structure like this, right? Now there was a reason for me to convert both the lone pairs from nitrogen here, because there was 2 negative charges here, right? When I convert one lone pair into a bond pair, 1 negative charge goes away and this 1 positive charge goes away, so this becomes 1 minus and 2 plus. So you would have thought, oh, I can convert one of these. Yes, you could have, but we learned that when it comes to keeping negative charges, keeping a negative charge on a more electronegative element is better compared to keeping the negative charge here. Having it here is better. So the Lewis structure wise, this is the most stable Lewis structure. Is that clear? This is the most stable Lewis structure. Now some of you would have drawn this, some of you would have drawn this. This could be a actually you can draw this as a resonance structure, right? You could have drawn this separately as a resonance structure. Anyway, we are getting to this resonance structure later. So you would have drawn, some of you would have drawn this. This is not the most stable Lewis structure. Lewis structure wise, this one is somewhat unstable. When you are asked to draw just a single Lewis structure, you always draw the most stable one. right? In the more stable one, the negative charges should be present on the more electronegative elements. So the negative charge here is should be present in the more electronegative oxygen atom, right? This is not wrong, this is not very unstable. Instead, more than this happens to be more stable. Do you understand? There's a correct way of doing things, and there's a, like, shortcut method of doing things, right? Sometimes the shortcut method is not very long lasting. Example, sometimes, like, asking your friends right before the, like, exams, semester exams, you ask, okay, what kind of questions did the teacher say will come, and then you somehow, like, study those and pass really well, like term test exam 75, 80, 90, my goodness, right? And then you don't study that well. But for the final exams, can you do it like that? A levels? No, you have to have a consistent, good, studying approach. You should have a good recollection of the things that has been taught to you. Without that, you can't perform really well, because at the exam you don't know which questions are coming. No, we can predict, teachers can predict and tell you, but does that mean our predictions will always appear in the paper? Unless and otherwise we are related to whoever who's making the paper, I can't be sure and tell you. Not related, like they call and say, Rakita, this question is coming, give it to the students. Then of course it will be clear, but we can't always be sure of that, right? So what I'm trying to say here is, this one happens to be the most stable. This is also stable, but not as stable as this. So when a question asks you, draw the Lewis structure, but in our structured papers, they are very clear about the terminology. They don't just say draw the Lewis structure. In the structured paper, they say draw the most stable Lewis structure. Then obviously this is the most stable Lewis structure, not this. Understood? Right, so take down the second one. So this is not the one, this is the answer for that question. Right? Can write second one. Apart from the Lewis structure drawn above, draw two other resonance structures for this molecule. Draw two other resonance structures for this molecule. To the same question, please write. Show the electron transfers. Show the electron transfers. And comment on the stabilities and the contribution of each resonance structure towards the resonance hybrid. Each resonance structure towards the resonance hybrid. Here they are not asking for the resonance hybrid. Okay, this question doesn't ask for the resonance hybrid, but rather you have to comment on the resonance contribution towards the resonance hybrid. we'll call this structure A, B and C. It will be easier. A, B and C. I haven't completed the B and C structures. Electron transfers you have to show. If you need any help. Now what you have to do is you can think මෙතන තියෙන lone pair එකක් මෙතනට එන්න පුළුවන්. ඒතර ඉතින් මේ nitrogen bonds පහක් තියෙන්න බෑනේ. මෙතන එකක් ඇරිලා මෙතනට යනවා. මෙතන එකක් එනවාට. හරිද? ඕන ඊට පස්සේ තව එකක් ගන්න. මේ bonds දෙක මේවා දෙකක් එන්න පුළුවන්. ඒතර මෙතන දෙකක් ඇරිලා මෙහෙට යනවා. තේරෙනවද? You have to think like that. Okay? So, since they are asking you to draw two more, one of them could be a bit unstable, right? Because they are forcing you to draw three, no? So that means one could be unstable. Now, since I have already shown you one, I will show you. Now, pay attention, students. I want you to be able to think this way. I will give you some questions next week. In the sense past paper questions based on this. So pay attention here. So I will not move on to the other part without discussing some questions next week, right? So now pay attention. What we can do is these lone pairs we can turn, these bond pairs we can turn them back into lone pairs. Right, so the lone pairs over here we converted into these bond pairs. So we can convert them back to lone pairs. So for example, we can take one of these bond pairs and turn it into a lone pair. And while doing so, one lone pair from nitrogen oxygen can be turned into a bond pair. Or you can think of it this way also. This atom has enough and more lone pairs. We can convert one of the lone pairs into a bond pair. So nitrogen can't be having 5 bonds, right? It is not capable of having 5 bonds. So that means one bond should break, and this broken bond is given to nitrogen atom as a lone pair. Is that clear? When I'm giving from this side, it takes one of these bonds and break it and give it to the other side, right? One gives, the other one breaks and gives electrons to the other atom. Clear? This gives electrons over here. Nitrogen forms a new bond. Nitrogen can't have 5 bonds. One bond breaks, gives one to the other nitrogen atom. So then it results in this. It results in this. Are we clear? Right? So now this is less stable than that, but still okay, not too unstable. You have, like, negative and a positive. If they were both the same charge, it will be very unstable, right? Having positive positive. Luckily it is not the case. Negative and positive, somewhat okay. The only problem is the more electronegative element is neutral and the less electronegative element is negative. So regardless, this is a somewhat of a stable resonance structure, not unstable completely. Now we have to draw another one. So we can do another thing. You can take one of these lone pairs, again convert into bond. When you do that, nitrogen can't have 5 bonds, so one of these bonds should break and give electrons to the other nitrogen. So I can show you this. And this bond will break and give electrons to this nitrogen. So when you do that, you have one lone pair on oxygen. There will be triple bonds between nitrogen and oxygen. And nitrogen has only one single bond. And nitrogen would have 2 negative charges. Yes, nitrogen would have 2 negative charges. This nitrogen would have a positive charge, and this will also have a positive charge. That oxygen will also have a positive charge. Is it understood? So therefore, students, then we can comment on the stabilities. We can say this is the most stable. Most stable. This is stable. This is unstable, or we can say least stable. Less amount of formal charge, and negative charge on more electronegative element. Now this one, now I'm just writing why we consider this to be very stable. There's not a huge charge separation, like only 2 formal charges are there. Here also the same thing. I can write the same thing. Not a lot of formal charge. However, you can write not as stable as A, because negative charge is on a less electronegative element. This one is least stable because it has a greater amount of formal charges, So the formal charge now amount is much higher. Adjacent atoms have similar charge. Adjacent atoms have a similar charge. And the other thing is more electronegative. More electronegative oxygen atom has a positive charge. These are all bad things, right? These are all bad things in a sense. They are basically contributing to it being less negative. Less stable, not negative, less stable. So this is something to keep in mind. It's too cold now. Now that thing works, I think. Did you understand this, students? Clear? So you have to keep an eye on for why certain structures are less stable. We don't want a huge amount of charge separation. Actually, having a large formal charge on single atom is also a bad sign, right? Like -2, -3, those kind of large charges on a single atom is also a sign that it is not very stable, resonance structure. Apart from that, now in this case, adjacent atoms, like these are close by, adjacent atoms can't have similar charges, right? Positive, positive, not good at all, bad, right? So apart from that, a very electronegative element, the second most electronegative in the entire periodic table, regardless of that, like we always compare, no, this one is less electronegative here compared to oxygen. So the less electronegative element, the more electronegative element, oxygen, has a positive charge, extremely not stable, right? Having a more electronegative element obtaining a positive charge in a resonance structure is a good indication that it is not a stable structure. It's always a comparison though. Compared to this is more electronegative. So that means compared to this can't be positive, right? So if there is a negative charge, it should be present on oxygen. We have one more sentence to write before we wrap things up. Write down a small sentence. Write down a small sentence. Write down. Contribution towards the resonance hybrid is greatest. Contribution towards the resonance hybrid is greatest from structure A, as it is the most stable. Contribution towards the resonance hybrid is the greatest from structure A, as it is the most stable. Right? Then you can write contribution, you can write structure B has a less of a contribution compared to structure A. And structure C will have the least amount of contribution. Structure C will have the least amount of contribution. As it is the least stable. As it is the least stable. Is that clear? Now students, if you analyze past papers in the structured essay parts, this question is common, right? So we will do some structured essay questions, about 2 I will bring next week, because I don't want to take the entire class time to do only papers next class itself. I will do a separate class for that. So for next week's class, be thorough with these parts and come. We'll start with some questions and we move on to a part called dipole moment and polarity of molecules. This is a very important section. Please don't miss out because it is important to figure out how dipole moment works, right? So any questions before we wrap things up today? Anything? Okay everyone, so if that is the case, we'll wrap it up for today. And if you have any questions that you would like to ask, please drop a message on the group. So that will be all for today then. I'll see you all again next week, same time. Right? Have a good night then.